Hi guys, this is Sir Ernest and today we will work on a sample problem involving Lagrangian dynamics. So this is example 7.5 of Marion and Thornton, and the problem reads: the point of support of a simple pendulum of length b moves in a massless rim of radius a, rotating with a constant angular velocity omega. Obtain the expression for the Cartesian components of the velocity and acceleration of the mass m. Obtained also the angular acceleration for angle theta as shown in the figure. Okay, so in this figure, you can see that this is your pendulum bob, this is your simple pendulum, and this is your support. Okay, so this support moves with a constant angular velocity. Okay, and the radius of this rim is a. So that means this as the support moves in this motion in this direction, it undergoes a angular displacement with respect to the positive x-axis as omega theta. Okay, so in this case, m here will be, because this is a simple pendulum, this m on this length is defined by this angle theta. This theta is defined with respect to your vertical axis. Okay, so in this case, we first usually what we do here is we start with the relationship between the Cartesian coordinate system and your polar coordinate system. So in this case, so if we're going to drop a line here, this is actually x, and this is y. Okay, so from here we can get the relationship. X, as you will notice here, is equal to this. If we're going to drop a line from here, okay, so we have this distance and this distance. Okay, so x will be the sum of this distance and this distance. So the first part here, okay, so this distance would be equal to a cosine omega t. And then we add it with this length, which is b cosine theta, because if this is theta, this is also theta. Okay, so that's b sine theta. Okay, clear, right? So next would be y. So if this is y, we want to find this is actually equal to this length minus this length. Okay, so this length will be, because the direction is downward, so this is minus, this is positive, right? So this is this one, which is b yeah, so that is a sine theta, sine omega t, and then minus this one. So this is yeah, so this is minus b cosine theta. Okay? Okay. So from here, we can calculate the velocities. The velocities, x dot and y dot, is now equal to, so x dot is equal to, so we differentiate this with respect to time, and this one with respect to time. Because a and b are constants, omega is a constant, so this becomes negative a omega sine omega t. And then plus b theta dot cosine theta. Y dot, on the other hand, would be a omega cosine omega t plus b theta dot sine theta. Okay? So from here, we can now calculate the kinetic energy of the particle. Okay? So the kinetic energy of the particle will be 1/2 m x dot squared plus y dot squared. So we're going to evaluate this. So this is now equal to 1/2 m times square of this. Okay, so it's the square of this. The square of this x dot would be a squared omega squared sine squared theta. Sine squared omega t, sorry, plus b squared theta dot squared cosine squared theta minus 2ab omega theta times sine omega t cosine theta. Okay? Now, plus the square of this. So this is a squared omega squared cosine squared omega t plus b squared theta dot squared sine squared theta plus 2ab omega theta dot sine theta cosine omega t. Okay, so you will notice that we can simplify this as follows. For example, we can combine this term and this term, and then using the fact that sine squared theta sine squared omega t plus cosine squared omega t is equal to 1. So that means this is now equal to 1/2 m times a squared omega squared plus we can combine this term and this term, right? Which is b squared theta dot squared. And then we can combine this term and this term, right? Which gives us 2 ab omega theta dot times sine theta cosine omega t minus cosine theta sine omega t. So you will notice here that this term is actually sine of theta minus omega t using a trigonometric identity. So therefore, the kinetic energy is now equal to 1/2 m times a squared omega squared plus b squared theta dot squared plus 2ab omega theta dot times sine theta minus omega t. So our kinetic energy is a function of theta and theta dot, which are both functions of time. Okay? Now, let's calculate the potential energy. So the potential energy of the system is now written as okay, so the potential energy is now written as okay, so this is U equals mgy, where y is equal to a sine omega minus b cosine theta. So this is mg times a sine omega t minus b cosine theta. Okay, let me put it here and here. So you notice that the potential energy is a function of theta, and this is a function of time. So therefore, we can now write the Lagrangian of the system. So the Lagrangian of the system is now equal to this minus this. So this is t minus u, which is equal to 1/2 m times a squared omega squared plus b squared theta dot squared plus 2ab omega theta dot sine theta minus omega t minus mga sine omega t plus mgb cosine theta. Okay, so from here we can conclude that our Lagrangian is now a function of theta and theta dot, and theta and theta dot are both functions of time. So this tells us that we only have 1 degree of freedom. So you will notice that even if you have a complicated solution here, complicated configuration here, we were able to reduce our problem as a problem with 1 degree of freedom. Okay, so in the next video, we're going to solve for the equation of motion using the Lagrangian of the system. Okay, so I'll see you guys in the next video. Bye-bye.